en Agustín. ¿Vas a venir al final? ¿No te vas por ahí?
Después no va a poder grabar. Pero ayer no. Muy bien. Hubo problemas en el video, pero teníamos nada. Cada cabeza es 0.
Ah, sí, sí.
Before you start, for some we'll wait for you more minutes.
Yeah. A ver,
Sí, claro, yo también
Okay, it's a test. Can you hear me? No, for you. It's a test. Testing. Can you hear me? Testing. This will be fine. Let's start.
fill in this during the day, because at the end of the day I need to call in the restaurant and tell them the numbers. And also signing sheets, that's standard, so. That's it.
Okay, thank you. Good morning, everybody again. Before you rest yesterday. So, today we are going to talk a little bit about more or less short introduction to sustain dynamics, as I told you yesterday, and also a short introduction to the basic software. The purpose of this session is just to understand the methodology that we have been using in the William model, that is system dynamics. It's not only system dynamics, because we introduce another kind of methodologies like input-output table. So in the William model, indeed, there is a, let's say, a hybrid system with many ideas for system dynamics, but other ideas combining in the methodology with other kind of, let's say, modeling techniques and so on. So, but anyway, the main structure of the William model is just system dynamics. So I think it's interesting just to explain you what is the system dynamics basics. Obviously, this is a very basic introduction. So maybe all of you that are familiar with system dynamics or whatever will be a little bit boring, but this is, I need to start from the 0 point. Okay. And also we will try to, the second purpose of this the session will be also just to introduce you the basic knowledge about the benzene software, so you will be able to manage the more or less basic things in benzene software, at least in the free version, that is the PLE version that you have already downloaded, or if not, we will be able to download now, there is no problem. And in this sense, if you are able to manage the basic tools of benzene, you will be able to analyze any kind of model with benzene reader. So you will be able to analyze and to check everything, for example, in the Medea's model, William model, whatever. And also you will be able to develop simple models, okay? Indeed, the purpose of the hands-on session, I don't know if we will be able to do it or not, but we can try to develop let's say, simple model for this identity. Remember that Neven was talking yesterday about K-identity, so we can try to develop a model around the K-identity. So we will do it in the last part of today's sessions. And, well, I think we will be able to do it. You will do it by yourself. Okay? So this is the idea of the whole day. There will be four or five parts, indeed. First, an introduction. Then I will try to explain how is the modeling process. Then some fundamental modes of system behavior. This is one of the reasons we use system dynamics, trying to understand the behavior of the systems, all the things that are common for all the systems, even when they are social, technological, or economical, they have more or less common behaviors. Also, we will do some introduction to the benzene software, I have already said. And finally, we will try to do some exercise around the K-identity model with benzene. You will do the exercise. Okay? So, let's start with the introduction to system dynamics. Well, in this part, we will mention a little bit about the relation between system, modeling, simulation, complex system, the purpose of system dynamics, and just a small words about the history of system dynamics. Okay, sorry. Let's start with what happened? Okay, the origin of the system dynamics. During the 19th century and the beginning of the 20th century, most of the let's say, dominant philosophy to understand the world was mainly this kind of analytical, reductionist, and mechanical and unidirectional causal paradigm. That means that people understand that this is the cause and this is the consequence, the relation between two different facts. Analytical means that in that period the whole system was understood just like the sum of the parts. So if we have, let's say, this classroom, from an analytical point of view, we are just only a collection of many people, each individual, each table, each chair, and whatever. But nothing, just a little view about the relation between us. As you can imagine, from my point of view and from later point of view, is so much important not only the individuals, but the relations between individuals. So it's not enough just the analytical point of view of each part, but the relations, okay? Also, the mechanistic point of view in the previous, let's say, 19th century and beginning of the 20th century, just understand that, for example, any kind of complicated machines were just the composition of different elements, just things in a car. A car was just a part of engine, wheels, and so on, but not the relations. And also, the reductionist was the formulates that the basic laws are the laws for everything. However, in real systems, usually there are, let's say, a hierarchy of the systems. That means that it's not the same, the whole system, like a complete state with the government, that individuals, so the behavior at different levels are different. So, this is the point of view of the analytical, so we have different compartments for everything. And from this point of view, at the medium of the 20th century, approximately, start a new concept to understand the life and the system. The new concept was called the systemic science. The systemic science tried to give much more importance to the relation between the elements than the elements by itself. Instead of be analytical and reductive spirit of classical science, the systemic approach addressed the study of complex systems through the relation between the elements. So the relations gains importance in comparison with each element by itself. So it means that if in the classical science we only analyze in an experiment, for example, what is the cause, what is the effect of a certain fact, of a certain experiment, in the systemic science, we try to analyze the whole system. So in this whole system, there is not only one relation, but appears a lot of feedbacks and another relations that give to the whole system a different overview. So in this kind of whole system, usually appears feedback. So we cannot consider an isolated relation between two facts, cause and effect, but we have to consider all the system and all the relations like a whole. So this is just a funny example. It's not only just to push some paces, but sometimes appears the feedback. Well, there are more kind of examples of this. A very clear example of what I have been talking is just ecosystem. Ecosystem cannot be considered like the sum of different elements. One animal, another plant, another animal, the air, whatever. But the relation between all the elements. This kind of relation may be quite different, includes, of course, symbiosis, parasitism, predation, competence, and so on. Also appears, for example, the exchange of matter and energy, this kind of flows, and also hierarchies in the regulation of the systems. For example, nobody will think that ecosystem is just something like that. 8 kind of plants, some the head of an animal, another head, some legs, whatever. It's not this. This is not an ecosystem. This is the analytical point of view. How many things I have in ecosystem? Just counting. So this is the classical point of view. Why the ecosystem point of view? The systemic point of view is just to understand that everything is related each other. So the relations are even more important than the elements by themselves. So, so in this kind of, let's say, systemic point of view, we consider obviously also the components, but mainly the environment, the structure, and the mechanism. The mechanism standing as the process that make that the system works. So, some definitions that maybe you already know, obviously, but I need to be clear. What is a model? A model, in general way, is anything that represents a thing. You can consider many different types of models. For example, you have a small plastic car. This is a model, a physical model of a real car. If you have a picture of somebody, this is a model of the real person, for example. Okay? We have different types of models. We have mental models. Mental models is that idea we have about something. We have a mental model about, for example, what a university is. I think university is a mix of teachers, professors, students, buildings, something like that. But then we have also formal models. Formal models is something that you have built with some basis. We can have physical models, mathematical models, and so on. Nowadays, we are going to work mainly with mathematical models. So any kind of system dynamics model is going to be a mathematical model. In the field of mathematical models, we have a very broad type of mathematical models. Every day, all the days before, we have been talking about some, yesterday I guess, we were talking about mathematical model to optimize, and so on. So, in our case, we are going to develop a mathematical model with the final aim to simulate the model in a computer. So, some of the principles of the mathematical model will be just to be able to get simulated in a computer. Okay? So, does it mean that it should be discrete and so on? Well, this is a typical examples of models, just a small plastic or whatever car, and this is a mathematical model, in this case of some differential equations about whatever. This is also a typical model of motoring, electrical motor, for example, in that case. And we have to understand the difference between two different types of models. One type of model is that we call black box modeling. Black box modeling means that they are based mainly on data. So we have data and we try to find any kind of equation that is able to fit as near as possible to this data. So the main source of knowledge in the black box model are the data we have. As is not so relevant what are the physical or the law that govern this process. Just the attention is just in the data. For example, some of the models, not this one, but have been using for some purpose this kind of black models. Maybe you know are neural networks. Maybe you have been told about neural networks are trying just to understand what are the input data and the output data. So you put together and they say, okay, this is the representation, but why? I don't know, but it runs, it works. So this is a classical example. Obviously there are much more. Also we can have just a black box model if we decide, okay, this is the system, and I decide that this is going to be the structure. Why? I don't know why, but this is going to be the structure. So I try to feed all this data with this structure. This is a second order equation. And I find that the best parameters to fit with this equation are this one, 1.43, 23.4, and so on. Okay, why? We don't know, but it works. So this is not the way we are going to do the things in system dynamics. Maybe it does work with many things, but this is not our way. Wow. I don't know what happened. Oh,
Black box.
something connecting. Something.
It's in your computer.
You don't know what's happened here. Connecting. Do you know
The connection.
the connection? Don't do anything.
Aha. So the connection broke. You should connect it back.
Promijenimo možda Wi-Fi network ili ima nekoliko kaseva, samo da promijenimo.
So anyway, I can go ahead. And the other type of system, the other type of models are the white box model. The white box model are based on knowledge. So what we have to model is the real knowledge we have about the system. So does it mean that the starting point of the model is the knowledge about the relations between the parts of the model? So instead to take already data and put together, we start with the knowledge that we have about the system. For example, if we talk about CO2 emissions, we don't put all the CO2 emissions and any other variable. I remember to watch some maybe interesting papers or maybe interesting research works in which they put CO2 emissions and any other variable. Any other variable, maybe ice cream sales, or maybe tobacco, or maybe whatever. So they find that there is a correlation and say, okay, CO2 emissions is mainly due to the ice cream sales. Why? Look at the table. Okay, well, maybe it's interesting. Obviously, I respect everything, but this is not our way. Our way is just to say, what is the origin of CO2 emissions? And the CO2 emissions are due to some fuel combustion. And what kind of fuel combustion we have? Sorry? So just a minute.
Yes.
And now silence. Okay. So, well, I was explaining a little bit that we try to do our modeling based on real knowledge about the systems. This is the way we are used. Obviously, after we establish some kind of structure or relation between variables, later we will need to look for data to check how this data fit with the knowledge we have. So obviously we also will need to use data, but the data comes, let's say, after that, okay? After the structure. We find the structure, the real relation, and then we look for what data will be able to fit or to explain this knowledge we already have. This is the way we will try.
So,
Yes?
what if the data does not fit well the model?
Same, maybe we have to check the knowledge we have about the system. But the knowledge means that you have an hypothesis about the relation between the things. So the hypothesis should be based on the knowledge you have, maybe experts, maybe whatever, any natural law, any physical law, whatever. Then you try to fit with the data you already have. And if you don't find that this is a good relation, you need to ask why it doesn't happen, why I have forgot. Maybe if I forgot something that I need to include, okay? And review again. This is the process, not just put together and see, okay? So, the other ecosystem dynamics are two kinds of typical objectives. One of them is just to analyze and understand complex systems. This is by itself an objective. That means that if we are able to model a system and we find a model that is a good representation of the real system, it means that we have already understand the system. So we can test the model on simulation, trying to check what is going to be in the real system. So just to understanding a real system, maybe an objective of the system dynamics. By this way, we can understand what is the feedback, the tipping points, delays, and some of the topics we will see later. And the other objective, general objective of course, is just to use the models. Why? The use of the models usually is oriented to take, I will modify the word instead to say take optimal decisions, just to take the best decision, the best possible decision. Why? Optimal is a very ambitious word. So it's a mathematical definition of what is the optimal. Okay? So in social systems, social or complex system, it's difficult to talk. And this solution is based on the knowledge that we have available. What does it mean that some mentioned the last day about very high uncertainties, and we have to work with these uncertainties. But anyway, we have to take decisions. So even when we don't have all the knowledge, we need to have decisions. So this is a way to help in the decision taking in order to, well, solve the problems. And also, we can try to anticipate scenarios. Okay. So, I mentioned the word complex systems. Obviously, for simple systems, we can more or less understand easily, and we don't need to build a big model, just to understand and to take decisions. But when the system is too complex, we need the help of this kind of simulation tool in order to take decisions, because it's quite difficult to understand with a mental model what is going to happen. Some relations are not so intuitive. So for those systems in which the relations are complex in the sense of several feedbacks, are nonlinear relations, for example, delays and so on, it's much better to have a simulation tool that helps us to understand what is happening than just to have an idea about what is the best. Let me use just a very simple example. In the case of Spain, many years ago, there were a lot of doctors, so somebody decided, oh, we have a lot of doctors, we don't need to have more doctors in the faculties. So there were a decrease of the doctors an abrupt decrease of the doctors. And now, about 10, 20 years later, obviously there were no students of, or less students of medicine, and we see that there are not enough doctors, so we need to hire new doctors from other countries and to check how to do it. So why politicians doesn't understand the problem? Because they think just in this very short term, what is happening today, not what is happening in the next days. So obviously there is the medicine faculty that we have today and the doctors we are going to have in the next 10, 20 years. So if we don't have with this kind, if we don't think with this kind of delay, we can have some mistakes in order to plan some, in this case, strategic decisions or whatever. What are the causes of complexity? There may be different causes of complexity. One of them, obviously, is the number of variables. When we have a lot of variables, it's difficult to understand what is the relevance or the importance of each variable. This is our case in the case of climate change. Obviously, when we think climate change, people think, we need more renewable energies. Of course, we need, but it's not only a problem of renewable energies. It's a problem of our economy, our behavior, a problem of the materials, a problem of what type of energy we need, the time we need to build new plants, and so on. So we extend the number of variables, and then in a certain point we say, I am not able to understand everything. What is most important? Is most important to switch off the light here, or it's much more important to take the bicycle, or it's much more important a wind farm, or whatever. So how to decide what is the most important? So when we have a lot of variables, it's very difficult to understand all the things. That is the case that we are going to use for integrated system models, a big model. I mentioned yesterday that in the case of Medeas, that is more or less small. It has about 6,000 variables, more or less, and William has more than 2 million variables. So it's very difficult for anyone to understand in this mind how is going to behave a system with so many variables. Nobody can predict. So this is a clear reason of complexity. And the second, what is quite related, is when we have a big number of relationships between variables. And in our case, it's also the same. We not only have a lot of variables, but also a lot of relations between economy, environment, society, technology, whatsoever. So it's difficult to understand all these kind of relations and all these kind of feedbacks. Also, another reasons of complexity may be the delays. I mentioned the delays between the students that are preparing to be doctors and the real doctors we have working, but not only, of course. Also to understand the time scales. Yesterday in the Nevel session, we tried to understand something that is not the same, the daily or the hourly scale. For example, for renewable energies, maybe we can have in 1 hour a lot of wind, but in the next hour we don't have wind, we don't have sun, but in integrated circuit model we work with a yearly. So it's not the same to consider how much wind I am going to have during all the year. That may be enough, but maybe in all the year we have a lot of energy, but not this day at this hour. Maybe one day at 1 hour there is no wind, no sun, no sun, so it's quite difficult. So the time scale is a very relevant problem for complexity. And also, obviously, the dynamics of variables, the evolution rates, and feedback loops. Also, another reason of complexity is the nonlinear because I think he always mentioned at the beginning that system we have a very clear way to optimize. But when we have non-linear systems, non-linearities are much more difficult to optimize or to find a solution, even in a differential equation, for example. So, and the behavior is quite difficult to predict in a non-linear relation. We will see some examples later. So, well, this is an example, but I'm going to go ahead. Feedback loops. Well, this is the usually first relation that every course of sustain dynamics show is the relation between the birds and the population. So this is a clear thing to work with. And this is the way we represent this kind of relation in sustain dynamics. That means that when we have birds, if we have more birds, we will have more population. But also, if we have more population, we have probably more birds. More birds, more population, more birds, and so on. So this is a very clear feedback. This is a positive feedback. We will call positive feedback, in which, if there is no limit, the growth of the variable, in this case population, not only people population, but maybe for rabbits or whatever, any kind of animal or whatever. If there is no limit, the growth will be exponential curve. And this exponential curve is due to this feedback. Okay? So this very basic feedback is going to appear in many systems. But in real systems, usually we have some limits, some saturation, and obviously it's not possible to grow until infinite values or whatever. So this is also a very popular and very easy to understand control system. In a control system, there is also a very simple loop. Imagine you have to fill just a glass of water with a tap. Okay? How does it work? You desire to have a glass of water with, let's say, half level of the glass filled with water. So you have a desired level. Then you think, you think what do you want, and so you open the tap. This is the actuator if you want. So this is the plant. You fill the glass with water. Then you watch, you see the level of the glass with your eyes, and then you compare your the level you are seeing, you watch with the desired level. So if the desired level is the same that you are watching, you decide, okay, I close the tap. If it's not, you decide, okay, I open the tap because I want more water. So this is a classical control loop, a feedback loop with a negative, I mean that a stable loop. So this kind of regulation loops appears not only in this basic case, but also in nature. In nature appears in all the system. Indeed, we have before human appears, we have a very equilibrium nature between all the species and so on. So this is a kind of control system. Go ahead. Oh, it's slow. Okay. Okay, sorry.
That's your return. You have.
Okay. So, let's explain one of the consequences. Often consequences are the oscillations. The oscillations means that the output of the system go like, I don't know if you have used already this kind of software with two tabs. One tab for hot water and one tab for cold water. Now, most of the but imagine you have this kind of two tabs, hot water and cold water. How you take a shower? Well, everybody do it maybe in a different way, but the most usual way is just to start with the hot water, the maximum, at the beginning, maximum hot water. So you wait for hot water, and then it burns, it's too hot, and okay, maximum free cold water, and then, no, so maximum is too much, so the other, so you try to find a good equilibrium, okay? What is happening? That there is a delay between you open your tap and the water that comes to you is hot or cold, okay? Warm or cold, okay? So during this delay, you try to manage with the tap, but you don't get it. So you need sometimes to find a real equilibrium for temperature. So during this process, there is oscillation due to the delays. So delays has usually a consequence of oscillations. This is quite relevant because we can observe this behavior in many systems. Probably between the decisions of politicians and economic behavior. For example, you take to take a lot of things, but society takes more time, so then the maximum, so there are oscillations between the input and the output. So another reason of complexity is the nonlinearity of the systems. This nonlinearity appears in many cases, but for example, one very easy example to understand the nonlinearity is the relation between training and productivity. Obviously, you have more training, usually you have more productivity. Maybe for example, for this training on benzene software, or maybe for any kind of work. So, but is there the relation between productivity and training linear? Can we consider that more training, more productivity in a linear way? No, this is not. Usually at the beginning, you need much more time to learn, and you have a low productivity. I don't find what I have to do. You have to ask. You are very slow with the production of results or whatever. However, when you have, let's say, higher training, you have a higher productivity. So the relation between training and productivity usually is like this green curve. So at the beginning, you need much more training, but your increase in productivity is quite low. Then when you have a certain training, you increase your productivity very fast, but at the end, your maximum productivity has a limit. So you are very good with the productivity in anything, and you find the maximum limit. So this curve, this classical curve for relation productivity and training, obviously is non-linear. So we cannot expect a linear relation for this type of variables. Well, another reason of complexity and nonlinearity comes from accumulation and memory of the system. Many systems have memory for different reasons. The memory of the systems in physical terms, usually we call state variables. Maybe you are familiar. State variables represents the memory of the system. So what happened in the history. But in physical systems, this kind of memory may be the water that we have kept, maybe the how the soil, the history of the soil have kept the properties of humidity, organic elements, and so on. Our own memory, we don't have the same behavior with a lot of knowledge that without knowledge, and so on. Well, I'm going to shift these examples. Let's show you an example that we will see later with benzene. And by the way, I show you just the first ideas that we are going to use. This is a real example of benzene about the evolution of an epidemic. In this case, we use only three kinds of stocks. Stocks are like the memory of the system. This I have mentioned just now. So one stock will be the people that are susceptible to be ill. So susceptible population is one stock. Another is the people that are already infected, infectious population, and all the stock will be the recovered population. That means that some people that are susceptible to the infection, one day, according to the infection rate, will become infection, and some people that are already infected will become recovered. So this is a classical flow diagram that we are going to see later on benzene. So at this point, just to mention that these kind of stocks or memory of the system are represented by rectangles. Okay? We will see later this kind of examples slowly. This is another example that we will see later. In this case, we have a, let's say, simple ecosystem with two types of stocks. One stock is for deer population, and the other stock is for food, the food that deer eat. Okay? So, we have a certain population of deers, and this population increase according the growth rate, and decrease according maybe the natural death, or maybe because of the predator population, the predators of the food we have. The food usually represents, in this case, the carrying capacity that will limit the deer population in the real systems. But the food also, and have also a food consumption rate. The consumption rate will depend, obviously, on how many deer we have. So this kind of diagrams is the one where we use later. Just a previous example. Well, this is another much more complex example. In this case, it was indeed our first big model, we call walling. And but the first part. Things here. Okay. Wait a minute. It goes very slow, the reaction. No. Okay. So, just to mention some relevant bibliography about system dynamics in history. Well, before bibliographies and notes about the history, system theory, maybe the first well-known book about system theory was the one about general system theory by Ludwig von Talanfi. Later, in the middle of the 20th century, Jay Forrester from the MIT Sloan School of Management developed the basic tool for system dynamics. and he wrote several relevant books: Industrial Dynamics, Urban Dynamics, and maybe the most well-known work of Jay Forrester, with also meadows and rangers, was the limit of the growth and the World 3 model. By this time also was developed the first language of system dynamics that was simple. Simple was the name, and later Dynamo. It's too slow. Yeah, there is a relevant delay. Okay. So nowadays, the more well-known commercial software for system dynamics is not the only one, but the most relevant are three. Benzene, that is the one we are going to use, but also Stella and I think is more or less the same, and PowerSync. There are some differences, of course, between all of them, but all of them are able to do more or less the same. For example, in the University of Norway, where Ole is working, they use mainly Stella, but we have been able to translate from Stella, well, we have been able with much work, from Stella to Benzene. In theory, there is an automatic translation from one to other, but it doesn't work. The automatic translation doesn't work. And PowerSync is another kind of software.
What about Simulink?
Simulink is completely different. Simulink is a part of MATLAB tools, and obviously you can simulate everything, but it's not oriented to system dynamics. It's just oriented to simulate any kind of technical system, whatever, but it's completely different. No. These are the software that are oriented specifically to system dynamics. Okay? So, about the books, obviously there are a lot of books about system dynamics, but if I need to recommend you some books, I will recommend you these two. One from John Sterman, that maybe is the most well-known book in system dynamics courses. And even while the title is Business Dynamics, it's not only for business, it's just for everything in system dynamics, don't worry. But the title is that because he published in the management school of MIT. And the other one I like a bit more, and it has a lot of good examples. It's from Andrew Ford, Modeling Environment. Well, Modeling Environment, this is the first edition, but there is a second one. This is the first and the second one. I don't remember exactly what is the year of the second edition, but obviously later. Well, well, some tasks that you already done, I think, but if not, we have time to do now. Is just go to the web page of Benzene. Everybody has already downloaded the Benzene software, PLD. You yes, you not, you yes.
Yes.
Somebody doesn't it? Nobody? So you can do it yourself. Just go to this web page and download. Well, you can go to download web page and you can download only the PLE version, which is free for students, and also Benzene Reader, that is different. We are going to use Benzene PLE Reader, Benzene PLE, in order to build our own models. We will try to build some very easy models here in the course. And we will use Benzene Reader to be able to read much more complex systems, models like Medeas or William. So you will need both. Okay? Even when we are going to talk about Benzene software with classical samples and so on, obviously you can use the Benzene help, Benzene documentation to learn by yourself. It's a very good documentation with Benzene help. Also, there are many examples in the software, Also, there is a user guide with tutorials and so on. And obviously, there are also some very interesting tips in the reference manual. So, this is all for this session. When is the break? I can continue, isn't it?
We have coffee break at 10:45.
Okay, so
Yeah.
I have time for the next. So, go to the next topic.
Professor, one question here.
Yes, of course.
I was wondering, you have talked about two different approaches to modeling, the black box and the dynamic. Is it possible to work with both at the same time? Does the locomotion project work with both?
Well, I explained, let's say, the different types of modeling in theory. In practice, you do what you can and what you prefer. So obviously, the things in practice are not so clear, so understandable, so on. In the case of locomotion, or maybe most of the models, in practice you have a mix between all types of modeling. I try to emphasize the relevance of knowledge-based modeling because I think that the black box modeling is quite dangerous because maybe you model something that you don't understand what that's inside, and this is very dangerous. To say, okay, well, I have a lot of examples, but well, don't worry about the examples, there are many of them, but when you try to find the relations just in a black box modeling, you can find real wrong relations that are maintained for a while, for certain circumstances, but you are not understanding what is going on. So even when you use knowledge-based modeling, you will need data, of course. And maybe if you are not able to understand all the things with the knowledge you have, maybe you will need to use some kind of black box modeling sometimes. But try to avoid as far as you can. This is my point of view. I don't know if this is an answer. In practice, everything you put all together. But as far as you can, try to understand the things before modeling with data.
I'm trying to understand where econometrics fits in all of that. Because econometrics, it can be a model at some point, because you download like historical data and just produce a model that fits.
Yeah.
So how does it work to use econometrics in system dynamics?
Within the econometrics, there are both, and a big part of the energy that people who do black box modeling is to then come up with a white box model that gets the same results to understand the dynamics within the black box. So most like machine learning research is about trying to find out what the machine did in econometrics, I would say, falls in both categories. They have a theory, but the theory is shit. So they claim it's a white box, but the theory is.
I also think the same in econometrics. Usually most of the models of econometrics start from an economic theory. So this is my economic theory, from Malthus, from Smith, from whatever. So I am going to prove this economic theory that is supposed to be knowledge with data. So the starting point in these cases are knowledge, at least hypotheses. Then they try to prove, and they say, okay, it does work. Or usually they try to force the things to work, even avoiding data that it doesn't work. Okay, so but in other case, obviously, econometrics just any kind of econometrics is possible to do just with a black box modeling also. So I don't know if we have answered your question or not.
Yes. I think that with an example, it will get clear.
There are many examples in econ. Well, I am not very friendly with econometrics models, but in the case of William, obviously we have many econometric functions and many econometric models. Manuel know quite well, and on Friday Iñaki is going to talk about that. But I insist it's not the same to this kind of econometric models that start from at least one economic theory and say, okay, economic theory says that the price always reach an equilibrium. That's an example. So this is a theory. So you try to show that this is true with real data. If you don't find that it's true, you have to come back and say, okay, maybe I will need to change my theory. This is the way.
But I mean, just thinking out loud, economic theory postulates a relation between consumption and income. But then, what's the size of this relationship? Which is the coefficient in which the income affects consumption? This can come from empirical studies or from that. So you can estimate parameters and then.
Yeah, of course. In any kind of model, it's an econometrics, system dynamics, whatever, black box or modeling. Finally, you will need probably some kind of statistical methods to fit your parameters. Obviously, finally, you need to do a regression, linear regression, or whatever, but you will need to fit which is the best parameter, the optimal parameter for this equation. Just the difference is the starting point. Knowledge of just data, but you need statistical methods anyway. We use a lot of statistical methods to fit all the dynamics models. Okay? Okay, let's continue with the again. The presentation there.
That computer obviously works okay.
Yeah, it's stable. Everything kind of lives in the network and it's like you change that.
Okay. Okay, go ahead with the next step. The next step is the modeling process. In this topic, we are going to talk a little bit about the problem articulation, formulation of hypotheses, some basic tools for modeling, inference diagrams, feedbacks, and the main type of variables that will be stock, flows, and auxiliary variables. So,
And there is still
no is okay. There is a delay. Oh. Maybe I can put just my presentation in your computer.
Yeah.
Because not going to be all the time. Okay, sorry for the interruption. Okay. Okay, so some clues about some tips about the modeling processes. So let's start with a definition of John Sterman. Many of the graphs, samples, and definitions I'm going to use here comes from the book that I mentioned of John Sterman. So first, the definition said that the art of model building is knowing what to put out and the purpose of the model as the logical knife. This is very, very relevant because how complex should be a model? A model should be as complex as we need just to solve the problem we want. So, just for example, in order to be a decorative element, a very a small model of a car, plastic car, may be enough, okay? But if you want to see how the car works, you will need to put in the car a small engine and something more. So, how is the complexity level we need? It depends on the problem we want to solve. And the problem will always drive the model. This is quite relevant. So, in our case, we want to solve the problem of climate change. So, it is the driving force of what we need to model. If you remember yesterday, someone asked to me about what model to use yesterday, Medeas or William. And I said, it depends what problem you want to solve. So it's not one model better than the other. It depends what do you want. Even for some purpose, we are going to use later the Calle identity model. Maybe it will be enough for some purpose to understand, for example, the role of energy intensity or the role of CO2 intensity will be enough. Okay. So don't think that not necessarily.
I agree.
So, and the second idea that is quite relevant is about always model a problem, never model a system. Okay? So we should think into the model, into the problem, not into the whole system. So there are these five. Obviously, the starting point is the problem we want to solve, as I mentioned. Then we need to articulate the problem. That means the boundary selection, where is the framework of the problem we want to solve. The second point is the formulation of hypotheses. These hypotheses are the starting point, as I mentioned in the case, for example, of economy, but not only, also in the case of energy or whatever, we need to establish an hypothesis. Then we try to formulate the dynamic model. Then we test. The testing, we will need data, of course, so to check if the model works like the real system. Then, if we have enough confidence in the model, we can say, okay, this model is a good one to solve my problems or the problems we have. So we can start with policy design and evaluation. So it will help us to decide what to do, and we will obtain results. Obviously, this is a feedback loop cycle, in the sense that maybe the testing is wrong, so we need to reformulate the model, or maybe we have to reformulate hypotheses, or maybe we have to change the problem articulation, because we will need to include something more in the model. So this is not only a linear process, but with several feedbacks according we find the solution or not. Starting with the first point, the problem articulation. The problem articulation means that we have obviously to define what is the problem and why is it a problem. Okay? This is a very obvious starting point, but it's necessary to have clear ideas about what is the problem. Then we try to look for key variables. Think, for example, just in the, let's say, simple problem that yesterday I mentioned, even about identity, CO2 emissions. Okay? CO2 emissions depend of, let's say, 4 very simple variables. Simple, what? Maybe population, economy, GDP per capita, energy intensity, and CO2 intensity. Okay? So this may be the 4 key variables. Also, we need to establish clearly what is the time horizon. It's not the same to solve a problem just for the next year or for the next week than to solve a problem for the next 50 years. So, in our case of climate change, we know that we have a very urgent problem, but we are not able to solve all the problems just for tomorrow, for the next year. So we have to solve the short-term problems, maybe, but we have to think also in the long term. Okay? So the time horizon is quite relevant. And finally, we have to define what are the dynamic problems. That means what is the dynamic behavior that we have been watching for years or for weeks or whatever, and this dynamic behavior is that we want to solve, to change. In our case, it's quite clear. We have observed that the CO2 emissions have increased during the last years, the CO2 concentration obviously has increased, and then it provokes an increase of the temperature and climate change impacts and so on. So we need to have these reference modes, and we need to see how we will be able to change. This is the problem articulation. Just a key tip about the client. Client, obviously, in a very general, from a general point of view. It's very important that when we develop this kind of system dynamics model, we should think in who is going to apply it, who is going to be the client in a general understanding. This is quite relevant because the client is not ourselves, usually. The client is not even the people who pays for that, but the client is the one that will be able to use this tool to change the things to solve the problem. For example, in the case of LOCOMOTION project, we receive the money from European Union and we have a project officer that check if we do everything fine, and he check deliverables and he check many things, but he's not the final client. The final client is the people that we will be able to use this tool to take the real decisions in the system. So our real client is mainly the stakeholders in government, in European Commission, and will be able to use this to take final decisions. So I should think in this client, not in you, sorry. Well, I am going to do an exception, but in this final client. In the case of William, it's true that we have different products, and one of the products, the final product, is just thinking in the educational system. So we want to, our client in this case is also a student, society, in order to be able to be easy to understand the real problem and to consider their participation in the solution of the problem. So we have different clients for different products. Indeed, we have 3 different products in LOCOMOTION. One for politicians, one for society, one for academia. So, so about key variables. Key variables we should classify in at least 3 different groups. One group, this is the most relevant group of variables, we call endogenous variables. Endogenous variables are those that will be represented inside the model, and they will have their own dynamics in the model by themselves. So they will be able to have real dynamic, and this dynamic we will need to check with the real dynamic of the real variables. Exogenous variables will be all those variables that we are not able to represent directly the dynamics. So we need to take like inputs of the systems. In the case of integrated assessment models, these exogenous variables are mainly what we call scenarios. So all scenarios are mainly all variables that we consider, let's say, hypotheses, and they will be the inputs of the system. For example, just a hypothesis or scenario may be how is going to evolve the efficiency of the photovoltaic panels in the near future. Somebody knows? Well, we can formulate an hypothesis that the efficiency of the photovoltaic plant, photovoltaic panels is going. Okay, this is a exogenous variable. I am not able to do any other thing. Or what is going to be the fertility of the world population in the next years? Well, nobody knows. So I need to formulate an hypothesis. The fertility of the population in the next years will be whatever. Okay? These are exogenous variables, and we will consider in the framework of a scenario. And obviously, always there are some excluded variables. Excluded variables should be something that we are not considering because they are very far from the deep of the root of the problem, so we don't consider.
Excuse me, Professor.
Yes?
How many variables LOCOMOTION project has to mention?
Yes. Nowadays it has 2.5 million.
Okay. Can you just estimate which percentage of variables are endogenous and which percentage are exogenous?
Let me think. Well, from these 2.5 million, more than 2 million comes from the economy model, from the input-output variable. So the number may be too big, but so exogenous variables, so maybe most of them So let me say that 90%, in this case, 90% of variables are exogenous. So we have only maybe half, less than 400,000 endogenous variables. This is, I have an account, but think about maybe even less, maybe 200,000 endogenous variables, maybe.
I was thinking, like, let me ask more specific question. GDP is seen as an exogenous variable or an endogenous one?
This is a very, very difficult question. Well, it's mainly endogenous. It's mainly endogenous. But we consider exogenous driver that we call, well, at least I think, that we call, let's say, desired or expected GDP growth. This is something that you look for. So you try to get, let's say, example, a 2% of GDP growth every year. This is something that you plan like this. This is your aim, your objective. But we have endogenous GDP, so depending how the things are going on, about energy, material, society, policies, whatever, you will get 2% of growth rate, or maybe you obtain minus 1% of growth rate. The second is much more probable. You will see with an example.
I was mentioning because the TENIEC, the Climate and Energy Plan for Spain, it actually assumed that the GDP is an exogenous factor.
Yeah.
So every assumption or every plan that is developed as a climate strategy for Europe is based on the idea that we are going to grow, but not because the models say that we are going to grow, just because we are going to.
Yes, I know that this is one of the, let's say, special things in William and Medea's, that we consider that GDP is endogenous and it depends on what we are going to do. And we have some conflicts in order to compare with other models, because we don't use these GDP exogenous variables usually. So the solution is that we use this exogenous GDP like a desired GDP, but then we obtain that we consider more realistic GDP. This is, and for example, some tests that we have already done in order to compare with other models, in the case of Medea, because William is still ongoing, so it's just to assume all hypotheses of other models, for example, for business as usual scenario, and check if with the hypothesis of other models, we also are able to reproduce the same outputs. And we were happy that we were able to reproduce the outputs of other models, but with some assumptions about there is no limit for energy, there is no climate change impact, there is no problem with anything. So obviously we obtain the same growth of other models. But we introduce some limits. Usually we obtain a real decrease of the GDP, even when the desired is different. So let's think about, remember this equation, this is the same. Indeed, it's the same slide that Neven showed you yesterday. We are going to think in this problem first to understand the theory, and later you will try to model with benzene this equation. This equation may be something more. Okay? So, if we want to, let's say, to forecast the CO2 emissions, the most simplest way to do it is just to forecast these four variables, as Neven mentioned yesterday. So we can try to forecast population, but obviously, as I mentioned before, population, nobody knows what is going to be the fertility in the next year. So nobody knows how is going to be the population. Maybe we can consider how is going to be the average life, maybe, I don't know. The second one is GDP population. As you mentioned, we can consider for that case exogenous because it's quite difficult to develop a complex model with endogenous GDP. For your case, maybe exogenous. Also, or at least maybe exogenous the GDP rate, growth rate. Also, the primary energy ratio in relation with GDP that we call energy intensity, or energy intensity is like the inverse of energy efficiency. And finally, the carbon intensity or emissions intensity. Okay? So we have here 5 variables that are related, and we will try to develop later a model. Maybe we will need some other variables, but they will be the 5 basic variables we will use. Okay? By the way, they are all data. One of the things I am going to propose is just to look for recent data for these variables. Just one part of the modeling process is just to look for data. So they are not very difficult to look for. Population, GDP, energy intensity, CO2 intensity, and so on. But as David mentioned yesterday, population is growing, and the expected projection is that maybe growing more or less, but growing anyway. GDP, everybody wants to grow. Most of the people wants growth in GDP. We have some decrease in the 28, and also we will have some decrease due to the pandemic that is not here represented. Energy intensity has been decreasing during the last years, in this energy intensity, but we are already in a very low values, so it's quite difficult to decrease a lot. Well, Neven is much more optimistic because he thinks that it's possible to decrease by a factor of 5. Factor of 5 here, for my point of view, is a little bit difficult. We have decreased more than 5 because we have started from a value of, let's say, 17 or something like that, and we are now around 2. But decrease a factor of 5 now is...
Sorry, do you allow a discussion on this? I am applying for discussion, if there's a time.
Well, maybe we can take just, this is to show, I don't want to try to, the discussion now, maybe we can later,
Okay.
Because we are going to model this.
Yes.
So in the model you can put what you want, okay? And maybe this, at this moment we will have the opportunity to discuss. But obviously I respect any opinion. Nobody knows how it's going to have the behavior of energy intensity, but the projection is like that. So, okay, let's go. By the way, this is the role of each of the factor of the identity of Kaya in the CO2 emissions. This is from the Carbon Project, maybe you know, it's a well-known group and web page, and here you see that the role of each of the factors of the Kaya identity, Kaya identity. Population is always, digamos, is nearly all the time increasing the CO2 emission, with the exception of this year, 2008, and pandemic. But in the other cases, it has been increased the CO2 emissions. And energy intensity usually has decreased the emissions, and carbon intensity sometimes have increased emissions. This is carbon intensity. Sometimes have decreased. So you can see times that increase CO2 emissions, times that decrease. So it's not clear the role of CO2 intensity. And CO2 intensity is due to the energy mix that is we want to solve with renewable energies. But historically, it has been not so clear this role. Okay, go ahead with the next step. The next step is just the formulation of hypotheses for the problem. So, in order to understand the problem, we need to understand what are the current theories of the problem, and what are the dynamic behavior of this the data in that case. So, what are the theories about CO2 emissions? This is about the main factors, population, GDP, and so on. And every of us can have a different theory, as Ilya mentioned. Okay, my theory is that we can decrease energy intensity, CO2 intensity, or whatever. So this is the theory we have to understand the problematic behavior. So we should try to formulate the problem as much as possible an endogenous problem. Why? Because endogenous is something that we can do anything about that. For example, I mentioned fertility as exogenous variable. When we consider fertility as exogenous variable, it's because we are considering that we cannot change the fertility. Okay? So it's something that we have like the framework, scenario, hypothesis, whatever. So if we want to change the things, we need to have endogenous variable able to change the thing from endogenous behavior. The third point is the mapping. Mapping means just to put all together the variables we consider. We can check now with an example or later a computer and try to see what is the relation between all the variables that we have. These kind of relations we will try to establish through what we call causal loop diagrams, boundary diagrams, or stock and flows or Forrester diagrams. Okay, so we try to draw all variables just to check, to understand how they work. At this point, we only draw the relation between variables with flows and names and so on. No equations at this moment. So, for example, can I move here? No. Okay, I use only. It's possible to go up the. No, it's not that. Don't worry. So, in the problem we have, just a map of variables will be, this is let's say the map of the screen, just to put on all the variables here. For example, CO2 emissions, CO2 concentration, energy intensity, CO2 intensity, population, GDP per capita, just a map. So in this case, it's quite clear. Energy intensity have influence of CO2 emissions, have a positive influence in the sense that when we have more energy intensity, we will have more CO2 emissions. Population will have also a positive relation. So when we have more population, we will have more CO2 emissions. The same for GDP, and the same for carbon intensity. And finally, when we have more CO2 emissions, we will have more CO2 concentration, and when we have more CO2 concentration, we will have more global average temperature. Okay? So, at the moment, these are the basic relations. So, this is the map. But any of you can find any other relations that maybe we can include?
Temperature will impact on GDP and population negatively.
That's very fine. This is the good one. If we have higher temperature, we can expect that we will reduce our GDP per capita. And if we have more temperature, we can expect an effect on population, increase of deaths, so something like that. Do you agree? We can think even more, but I think for our purpose, for the exercise we are going to do, this is enough. So, at that moment, we don't have not only the identity, but also a couple of feedbacks, and negative feedbacks. Okay? This is the structure of the model we are going to try to model immensely. Okay? Okay. Let's go with the next point. So, what are the causal diagrams? The causal diagrams are quite simple, as I have already shown. It means that when we represent X variable and Y variable, and we represent just flow from a flow, arrow, thank you. When we represent an arrow from one variable to another, means that this variable have influence on the other. When the influence is positive, means that an increase of the X variable will imply an increase of the Y variable. Just increase implies increase. We don't know if the increase will be linear, non-linear, or whatever. Just a qualitative relation. While we represent with a minus sign, means just the opposite. It means that set variable will affect W variable in the negative sense. That means that if I increase the set variable, the W variable will decrease. Also the opposite. That means that if I decrease X variable, Y variable will be decreasing also. Okay? A real example, yes? 5 minutes. Wow. Okay, thank you. So, if we have more birds, we will have more population. If we have more effort, we obtain more results, or better results. Well, this is the positive link and the negative links. We increase deaths, we decrease population. We increase sales, we decrease stock. In this step, even when it seems to be very easy, it's quite important to be, let's say, rigorous, in the sense of, remember what we were saying about black modeling and white modeling. We can find that there is a relation between ice cream sales and murder rate. And by a statistical point of view, I can say, okay, when the sales of ice creams increase, I obtain a higher murder rate. It's okay? What is the reason? Maybe there is a reason. If I have a reason, I can understand with knowledge that the average temperature, if we have a higher average temperature, probably we will have a higher ice cream sales, and also we will have a higher murder rate. But this is the, let's say, the knowledge way to explain the things, and this is only the black way to explain things, okay? This is a clear example of that. In other cases, we have no clear sign about that. For example, if you increase the price, are you going to obtain more benefits? This is a positive or negative. What is going to happen if you have higher price? Higher benefits or not?
Higher benefits for those who sell and lower for those who buy.
Well, but also if you increase the price, probably your sales decrease. So you obtain less. If not, everybody will increase price always to obtain more. So when we don't have a clear idea about the causal relationships, is that something is wrong. We cannot decide if it is positive or negative. So what we have to do something in this case is something like that. There are two ways. One way is obviously if you increase price, probably you increase benefits, but if you increase price, you decrease the sales, and when you have more sales, you will have more benefits. So you have two different lines of reasoning. By one way you increase, but by other way you decrease. So depending on the equilibrium between these two, you obtain finally more or less benefits. Okay? Well, also about feedbacks, I already mentioned the classical feedback between births, population, more births, more population, however. This is a reinforcement loop. So it will be unstable in the sense that if there is no limit, it will grow up until ever. But usually we have some limit with the food. So when we have, for example, in an island, a population of rabbits, and there is a limited quantity of food, obviously the food establishes the limit for the number of rabbits that can live in the island. This is what we call carrying capacity in an ecological system, okay? Well, I'm going to go a little bit. Well, this is another example of loop. In this case, we have some positive relation and negative relation. Let me check. When we have a quantity of CO2 concentration in atmosphere, we will have, as higher is the concentration of CO2, the higher will be the greenhouse effect. The greenhouse effect will imply a higher temperature, global average temperature. Then the global average temperature will increase the discharge expansion. The discharge expansion will decrease the photosynthesis of the plants. The photosynthesis of the plants, if it increase the CO2 in plants, and CO2 in plants will decrease the CO2 in atmosphere. So in this case, we have a loop with 1, 2, 3, 4 positive signs and 2 negative signs. These 2 negative signs, by multiply, convert in 1 positive. So negative by negative is positive. So we also can represent like that. Negative is like positive. So in this case, it's not an equilibrium loop, but a positive feedback. Positive in the sense that it increased a lot. More greenhouse effect, more temperature, more desert expansion, more CO2 in the atmosphere, more greenhouse effect, and so on. Okay? Well, we are going to stop here and come back after the break, okay? Well, if there are any relevant questions before the break, we can, okay, let's go for the break.